Hello everyone. In this video, we shall see how to design a transformer tank along with cooling tubes. When we start dealing with high rating transformers, power loss in the form of heat is a very important concern. So we have to somehow provide a method to combat this heating problem. So there are several cooling methods available. Here we are taking an example of cooling tubes provision, and I will be learning how to design cooling tubes. Design cooling tubes means how to find out the size of the cooling tube, number of cooling tubes required, and where to place around your transformer. Generally, the heat loss will be in the form of radiation and convection happening in your transformer. The transformer itself, uh, for some amount, the of heat will be getting transferred to the atmosphere by means of radiation. But what about convection? So, before going to that, a quick revision of what is convection and radiation. A quite simple example from your science, where you can see that the three forms of heat transfer. One is conduction, convection, and radiation. So in conduction, when you hold this, you will be getting the heat. That means the heat is getting transferred by the direct contact. So this is called conduction. And convection, if you see, suppose if you're producing heat here, the molecules start moving from bottom to the top, again from top to bottom. So because of the movement of these molecules, the water is getting boiled. So the heat is getting transferred by, there is no direct contact, but there is some movement of the molecules or movement of the coolant. So this process we call it as convection. And you know what is my radiation? There is no direct contact with the medium, but the heat is dissipated in the form of rays. So here, obviously, we are not going to use conduction method. It's not possible. So we will be preferring only these two methods. One is convection, another one is radiation. As I already told you, look at this picture of a transformer with this cooling with the cooling tubes. You can see there are so many cooling tubes available here. Section 1, section 2, section 3, like that. Now when you take this section alone, you have 1, 2, 3, 4, 5, 6 tubes arranged like this. Okay. Now each tube will be carrying some amount of liquid or any type of coolant. So what is the role these cooling tubes are going to play? So they are going to play in such a way that the heat dissipated is by means of convection. That is, they are going to carry the heat by methods of convection. Okay, but since if you see, this is your transformer, this portion is your transformer. Let me highlight this. Now this is your transformer portion, right? So by nature, there will be a heat transferring through this chamber, okay? Through this chamber, there will be heat dissipated to your atmosphere by means of radiation. So this is radiation effect, okay? And what about these tubes? These tubes is going to transfer heat by means of a convection method, okay? By convection method. But you should also keep in mind, see this portion of tube, no, these set of tubes are actually acting as a barrier to this chamber. So the radiation which are free to happen is getting affected by by this tubes arrangement. Okay, but even though this convection is helping us to provide an improvement in the dissipation of heat. So let us start the derivation by assuming some standard values. We know that the heat dissipation is carried out in two ways, namely radiation and convection alone. Suppose if I assume a plain tank surface, a plain tank surface will be having this amount of radiation in standard value. That is, you know what is specific heat radiation? It is a reference value. Okay, so specific heat radiation, that is amount of heat radiation by means of radiation concept is it is standard value 6 watts per meter square degree Celsius, and specific heat convection delta con is equal to 6.5 watts per meter degree Celsius. So in general, the total heat dissipation will be 6 plus 6.5, that is 12.5 watts per meter square degree Celsius. Okay. Now, what do you mean by tank? Say assume that this is your transformer. Okay, this is your transformer. Assume this is your transformer. Now, uh, and so this transformer will be covered by a tank consisting of the cooling tube. So this blue color which I'm drawing here indicates a cooling tank. Okay, so this is your transformer. This transformer is covered by a cooling tank, transformer tank. So what will be, suppose if I assume the area of the transformer tank as, suppose I'll take area of the transformer tank as ST. S indicates area and T indicates tank. Surface area, S means surface area here, T indicates tank. Suppose if I assume the area as ST, what will be the area of cooling tubes? So cooling tubes will be available inside your transformer tank. So they will be occupying some portion of your transformer tank. So what I can say is area of cooling tubes means there will be some amount of ST, that some amount I am denoting it as X. So that some amount I am writing it as X, hence I am writing it as X into ST. Okay. So what is the total heat dissipated by the tank? So tank means it includes your transformer, everything. You know the tank means that heat transfer will be both due to convection and radiation. So when you add these to 6 plus 6.5 is 12.5. So 12.5 times ST, that is the area. Okay, that will be your total heat dissipated by the tank. So what will be the unit here? The unit will be, it is watts per degree Celsius. This meter square will get cancelled here. Okay. Next, what is the total heat dissipated by tubes alone? So tubes alone means, that is tubes we are going to, tubes means it is going to contribute only by means of convection. So what will be the value? It should be actually 6.5. Why 6.5 means, why it is not 12.5? Because radiations are not considered here. So if I don't consider radiation, if I consider only convection, the value is 6.5. So 6.5 into, what is the area here? Cooling tubes area is only X into ST. So 6.5 into XST should be the answer. But as I already told you, these tubes are providing a very good improvement in dissipation of the loss. So what we are going to do is, it is actually performing more than its capacity in some or other. So what we are going to do is, we are going to give an additional of 35% area. Okay, so what I am going to do is, along with the 6.5 into X into XT, I am going to find addition of 35%. 35% addition means 100 plus 35. So it is 135%. Okay, so what is the expression now? It is 6.5 into 135 by 100 into X into ST. When you simplify, you will get 8.8 into X into ST. So this 35% is a standard value. Suppose if it depends on the application and the client specification. Suppose if a client is saying that, yeah, 40% is required, additional 40% means, then you have to put 6.5 into X into ST into 140%, that is 140 by 100. Okay, if nothing is specified, we'll take it as 35% additional value. Now the total heat dissipated by the tanks and tubes will be equal to 12.5 plus 8.x into ST. That means, see, this is the total heat dissipated by tank. This is the total heat dissipated by the tubes. So the total heat dissipated by tanks and tubes means you have to add these two values. So it will be 12.5 ST plus 8.8x into ST. That is equal to 12.5 plus 8.8x, the whole thing into ST. Next, what is the total area of the tanks and tubes? We know the area of the tank we have seen here is ST, area of tank is ST, and area of the tube is X into ST. So the total area of the tank and tubes means you have to add these two. It is ST plus X into ST plus S into ST, that is equal to 1 plus X into ST. Okay. So what is the total heat dissipated per unit area means you have to divide these two. Divide these two, we'll get this answer. Okay. Next, we have to keep into mind that we haven't included the temperature rise factor so far yet. Okay. So this temperature rise is the main reason for your heat loss. So we have to consider what is the temperature rise that is happening inside the transformer. Let me assume it as theta, and theta is equal to what is the total loss, and out of which what is the total loss dissipated, that is dissipated in the form of convection and radiation. So total losses including your iron loss and your copper loss, or Pi plus Pc, divided by how much of loss is dissipated by convection radiation. It is 12.5 plus 8.8x into ST. So when you rearrange this equation, you can get the value of X. So when I rearrange this, simplifying, I'll get X is equal to Pi plus Pc minus 12.5 theta st divided by 8.8 st into theta. What is the use in finding out your x? Initially, we have assumed the area of the cooling tubes as some portion into st, that some portion is x. So I should know what is that some portion occupied by the cooling tube. So that some portion x is considered by taking into account the iron loss, copper loss, temperature rise, and also the surface area of the tank. And finally, we should know how many tubes we are going to use it. So the number of cooling tubes required is a basic formula, that is the total area of the cooling tubes divided by area of each tube. So that will tell you how many tubes or how much of tubes are required for this cooling arrangement. So total surface area of the cooling tubes is x into st divided by area of each tube is pi into dt into lt. Suppose if this is your tube, okay, now this is your length. Length of the tube is LT and the diameter of the tube is DT. So it is so more or like a cylinder, no? So what will be its area? It is pi into DT into LT. So that is your area of each tube, okay. And this diameter, you should always I mean, if diameter is not, we are not able to find diameter directly, you can take it as 50 millimeter, that is the common value. And length of the tube depends upon the transformer tank, and there is necessity for space, spacing between the two tubes. Look at this diagram. You can see that there are tubes and there are spacing between each tube. Suppose this tube, there is a spacing between these two tubes and there is a spacing between these two tubes. Okay. So there is a spacing or a clearance required between the tubes. If that is not given directly, you can take it as 75 millimeter as a standard value. Okay. Next, at last we'll learn the dimensions of the tank. So now we have started with the necessity for cooling. So we found out the number of tubes and area of each tube. Area of each tube means then that means you already knew what is the diameter of the tube and length of the tube. So we are okay with the dimensions of the tube as well as the number of tubes required. Next, we should know what is the size of the transformer tank which is covering your transformer is required. So there we have to provide some standard clearances. Okay. Now look at this diagram. I have just highlighted the transformer with one color and the tank with another color. This orange color tells you the transformer layout. Okay, this we have already seen it. You know what is meant by capital D, capital D. And what do you mean by this H? This H is nothing but height of your transformer, which we have seen in the previous topic, right? Now, this blue color line indicates the height of the tank. So you can see this here. What is HT? So HT is nothing but height of the tank. Similarly, this WT is nothing but width of the tank. Okay. So what is height of the tank? Height of the tank will be equal to this H. Okay. Plus this space and this space. Okay. So if I take this as some clearance, let me take it as clearance. If I take this clearance as C3, okay, some value, clearance between this transformer and the top of your transformer tank. And similarly, there's this clearance, that is clearance between this bottom of the transformer and the bottom of the transformer tank C4. So what is HT is equal to? HT equal to, it is H plus C3 plus C4, and C3, C4 are said to be the, you can see the height of the tank of transformer HT is equal to H plus C3 plus C4. Next, see, this is your top view of the transformer. Now we have taken here a three-phase transformer. Okay, so this is a top view of the transformer. Now we'll find out what is the length of the transformer tank required. See, I want to find out what is this length of the transformer tank. So length of this transformer tank is equal to, you take this diameter. Let me name this as diameter DE, that is diameter of the external coil. So this is DE, and you will have two more clearances here. Let me name this clearance as C2 and the same amount here C2. So what is the expression now? It is LT equal to DE plus C2 plus C2. That is your length of the transformer. That is LT equal to DE plus 2 times C2. Okay. And finally, we will find WT, that is width of the tank. That means from this end to this end. So you know that there is some clearance on left hand side and right hand side. Suppose if I name the clearance as C1 here and this C1 here, what is the value now? This is your clearance. Okay, this portion is your clearance. Similarly, this portion is your clearance. So this is C1 plus C1 plus there are 2 times D. No, this is from this to this end, it is 2D. Okay, and here there is one diameter, that is half a diameter. It is, let me name it as DE divided by 2. Similarly here it is DE divided by 2. So now what is WT equal to? WT is equal to 2 times D plus DE by 2 plus DE by 2 plus C1 plus C1. So the final answer will be, it is 2 times D plus DE plus 2 times C1. So we have considered three phase transformer, so we are getting 2 times D. If you consider single phase transformer, you will not have three types of coils, so there will be only one D. So the same formula becomes D plus DE plus 2 times C1. So that's it about the design of cooling transformer, cooling tank, as well as cooling tubes for the transformer. You will get a more clear understanding of all these steps when you start working with numbers. Thank you.